Yes, assalamu alaikum, dear students. This time we are meeting again. This is lecture number 2. We want to deliver on this linear differential equation with constant coefficients. Previously, we discussed about this linear differential equations of nth order with constant coefficients and with variable coefficients, how we define it. And we have also done a very important theorem where we stated if y is equal to y1, y is equal to y2, so on to y is equal to yn are the particular solutions of the differential equation where right hand side is 0 with constant coefficients, then y is equal to c1 y1 plus c1 y2 so on to plus c and yn is also it is a solution that we did. Now we are coming on another theorem which is very simple one that will give you some clues about how we solve the linear differential equation of any order with constant coefficients. Now from today and onwards, few lectures we are delivering. It is lecture number 2. It will be the linear differential equations with constant coefficients. Remember, we have already told you that now we are coming to linear differential equations with constant coefficients. I will not write again and again that the constants, the coefficients are constants. It is understood. When coefficients become variables in case of the homogeneous linear differential equation and in case of the Legendre's differential equation with constant coefficients, there we will mention that variables or coefficients are variables, how we solve it. Okay, let us state here very important theorem one. It is this. I will state this first. This is the theorem. It states that if y is equal to v is a particular solution of linear differential equation, it is understood coefficients are constants. I will take linear differential equation of order n of linear differential equation. Let me write it d and y nth derivative dxn plus p1 dn minus 1y dx n minus 1 plus p2 dn minus 2y dxn minus 2 plus so on to plus p of n minus 1 dy by dx plus p and y is equal to x. Let us name this one. Assuming that y is equal to v is a particular solution of this differential equation and y is equal to u is the general solution of d and y dxn plus p1 dn minus 1y dxn minus 1 plus p2 dn minus 2 n minus 2 derivative y d of xn minus 2 plus so on to plus p n minus 1 dy by dx plus p and y is equal to 0. It is another differential equation with right side 0, and we assume that y is equal to v is the general solution of this. Then what is the conclusion? This is conclusion. Then y is equal to u plus v. Combining this, the solution of this, actually we are combining the solution of this, that is u, the solution of this, it is v. What is this? Then this y is equal to u plus v is general or complete solution of first equation, that is this equation. This is the statement of the theorem. Don't afraid of this, that statement is a bigger one, proof will be bigger. No, very simple. Actually, we want to give you something very important. When we solve the differential equations of any order, linear differential equations of second order, linear differential equations of third order, fourth order, when somewhere you have right side 0, sometimes you have function of x, how you solve it. You see, we took this differential equation, right side is, it is somewhere this function of x, that is x. We took that if this has a particular solution, y is equal to v, then what we do is same differential equation and take here this x 0, okay, and if y is equal to u is the solution of this equation number second, then combining this, the solution of this, get us combine it, y is equal to u plus v. In lecture number 1, what we did, please read that theorem. There we said we took this differential equation with constant coefficients. We said there if y is equal to y1 c1, sorry, y is equal to y1, y is equal to y2, y is equal to y3, so on to y is equal to yn, or n independent solutions of this equation, then there exists n linearly independent different constants. Okay, so that y is equal to c1 y1 plus c2 y2 so on to plus cn yn is the solution of this. Okay, that means this part u, when it is the solution of this differential equation, and in lecture number 1 we have seen the solution of this equation contains what, n arbitrarily constants which are independent. It is given by this u, because u is the solution of this when right side is 0. And when you find out the solution of this equation, it will now involve two parts. The solution of this will involve two parts. One part will be when you take this 0, it will be this. By lecture number 1, by theorem number 1 there, theorem number 1, we have seen what is its solution. It is given by this, and its solution, it is v. And we will give later on, after proving this theorem, we will be giving u one name and this v another name. That will help you for finding out the solution of the differential equation. And in maximum books they give you directly, the solution is given by y is equal to complementary function plus particular integral. Here in this theorem I am telling you just where and from which equation this u complementary function comes, and from which this the particular integral this v comes. I am just giving it is particularly for those students who are pursuing the undergraduate courses in mathematics or 5-year integrated courses in mathematics, and they have to just prove the theorem, prove the proofs. Then you can go to this working rule, this method of solution. Method of solution becomes very simple when you just learn this, understand this thing, and you just read it. For those students who are doing engineering courses, they should also see, just look into it, and then go to the solution. Let us go to the proof. Proof is very simple, you will see. I will go to the proof now. And I have named this equation 1 and this equation 2nd, and in the proof I will name the same thing. Let me drop this. Let us come to the proof. Equation number 1 is with you. I will write the proof in this way. This is the proof now. In proof you will write, given that y is equal to v is in fact particular solution of equation number 1. Equation number 1 you have in the statement. This means y is equal to v will satisfy that equation. What does this mean? This implies that dn, instead of writing y, you will write now v, dn v by dxn plus p1 dn minus 1 v dx n minus 1 plus p2 dn minus 2 v dx n minus 2 plus Pn minus 1 dV by dx plus Pnv is equal to x. This was your equation number 1, where we assumed that y is equal to v is a particular solution of this equation. So it will satisfy it. Name this now third. This is equation number third. Okay. Again, next you have y is equal to u being given solution of equation number second. Y is equal to v is the solution of equation number second. Now it will satisfy this u in equation number second, y right hand side is 0. So this means you will write this, it is nth derivative of u dxn plus p1 dn minus 1 u dxn minus 1 plus p2 dn minus 2 u dxn minus 2 plus so on to, this is p n minus 2 n minus 1, sorry, it is n minus 1 du by dx plus this is p and u is equal to 0. This is your fourth equation. Now I will prove that y is equal to u plus v is also the solution of equation number 1. Okay. For that I will find out, let us find I will find out of nth derivative of u plus v. That means I am replacing this in the equation. Let us find out d of nth derivative of u plus v with respect to xn, sorry, then plus p1 d n minus 1 u plus v dxn minus 1 plus p2 dn minus 2 u plus v dxn minus 2. Finally it is p of n minus 1 d of u plus v dx then plus pn u plus v. I am just finding out what this gives me. Okay, now you will use the fact derivative of sum of two functions is sum of their derivatives. It is a derivative operator, you can distribute it. Now derivative of u plus v is derivative of u plus derivative of v. So this implies that this is further equal to, I am evaluating this is d nu dxn plus dnv by dxn. This is plus p1 dn minus 1 u dxn minus 1 plus, it is very simple proof, dn minus 1 v dxn minus 1, then plus p2, it is d n minus 2 u dxn minus 2 and n minus 2th derivative of u d of n minus 2 v dx of n minus 2, so on, p of n minus 1, it is du by dx plus dv by dx, then plus p and u plus p and v. Now I will group the terms. I am just seeing when I replace this y by u plus v, I am finding out the nth derivative of u plus v plus p1 times n minus nth derivative of u plus v. I am using this result. Now I group up the terms. Group up means I will connect this with this u terms, this and this. So accordingly I will get, let me rub here, let us see, this gives me this is dnu dxn plus p1 dn minus 1u dxn minus 1 so on to finally it is pn u. Then plus I will connect this way, dnv dxn plus p1 dn minus 1v dxn minus 1 plus so on to it is your pnv. I am taking the u terms and v terms separately. Okay. Now this is your 0. What is this? This is v by third and fourth equation, by third and fourth. So what I am proving now? So I have proved this thing. Not v, sorry. This is your x, not v. This was by fourth. This is your x. This is 0. So in other words, I have proved this thing. I have proved now what I have proved. This implies that I have proved this thing, that dn of u plus v dxn plus p1 d of n minus 1 of u plus v dx n minus 1 plus p2 dn minus 2 u plus v of dx n minus 2 plus pn minus 1 d of u plus v dx plus pn u plus v. I have proved this is x. And what does this mean? This means y is equal to u plus v satisfies equation number 1. You look to the statement where we have named the equation number 1. There you have dn dxy p1. This is y, this is y, this is their y, this is their y. Yes, this is their y is equal to x. So this means this equation above implies y is equal to u plus v satisfies what? Satisfies equation number 1 in the statement. Do you follow me? You just look in the statement where this u plus v is our y. So when we use y is equal to u plus v there, you get this equation. So what does this mean? Mathematically it means that y is equal to u plus v satisfies first. So this implies that y is equal to u plus v is the general or complete solution of equation number 1. Now we have come to the conclusion, very important conclusion, that when we have to solve equation number 1, which was dn y dxn plus p1 dn minus 1 by dxn plus so on to pn y is equal to x, where p1 p2 so on to pn are constant coefficients of the differential equation, then its solution consists of two parts. One is u, another is v. Now we shall define from this equation, from this theorem, we define a new concepts here. This is u. The solution part consists of two parts. One is u. This will be called the complementary function, and this complementary function will contain an arbitrarily independent constants. If you again pose a question how, because in last time in first lecture we have proved a theorem Look that theorem. There we have said if y is equal to y1, y is equal to y2, so on to y is equal to yn are n independent solutions of the given then y is equal to c1 y1 plus c2 y2, so on to cn yn is also the solution. So this part is the solution of that equation where right side is 0. So that is the nth degree. It will contain n arbitrarily constants which are involved in this part. And this part will be called now particular integral, and this particular integral is free of arbitrarily constants. You may put a question here. You may ask me how you conclude that this part will be a part free from arbitrarily constants. The answer is very obvious, because we have said that the number of arbitrarily constants that the solution of a differential equation involves depends upon its order. So the order of our given differential equation first is n. The solution must involve n arbitrarily constants, but those n arbitrarily constants are here in this part. When n arbitrarily constants are in this part, you cannot involve again any constant in this part, because then it will contradict the very important theorem that it will contain more arbitrarily constants than the degree. That is not the general solution. The number of arbitrarily constants that the differential equation should contain depends upon its order. As you have seen in previous lectures, that the linear differential equation of first order degree will contain one arbitrarily constant. Now degree 2 will contain two arbitrarily constants. Degree n will contain n arbitrarily constants, and your n arbitrarily constants are involved in this. How will you involve the arbitrarily constant? No. So this part is also the solution, but this part is what? Free of arbitrarily constants, and this will be called the particular integral. Okay, so we will define now this complementary function and particular integral. Now we have very important definition. This is not important, important definition, and this definition is actually the deduction of the theorem which we just did, which is done now. Deduction of the theorem which we did. So we write the general or complete solution of dxn, and a derivative of y, plus p1, this is constant coefficient, plus p2 again I am writing this, plus p and y is equal to x. Yes, some students may put a question. Sometimes in class the students ask, but here you are not in the class, you are receiving the through online this lecture. They put a question in sometimes. We start this constants differential equation with constant coefficients. We start constants in general proof from here. Why not here? We are certain here constant is 1, because when we talk of the differential equation of nth degree, that means its coefficient is necessarily non-zero. Coefficient is necessarily non-zero. We can make it 1. When it is a non-zero number, we can divide by that number, and we get here in why we do is because the number of arbitrarily constants get reduced. When you are certain that the differential equation is of order n, so you can put the constant here 1. You are certain this cannot be 0. If it is some constant here, we can divide by that constant. If the number of constant is n plus 1, we can reduce the constants only by n by dividing this. This is the reason why we write here without constant. We start the constants from this. Even if this becomes 0, suppose if this p1 is 0, if this part is 0, then still the degree is of n. Even if every term is here 0, still this degree remains n. So we are certain here it is not 0. We take this 1 unity. Okay, this is clear. You may put a question, so I am clearing there. Well, we have now come to know the general solution of this is given by y is equal to u plus v. Now you will see, ask a question here, how we find out u. You find out u when you make this right side 0. Make this 0, solve it, you will get this u. Okay, how to find out this v? You have to treat it as x here. Write x again. It gives you a kilo. How we find out u and v? Because we there in the theorem wrote two different equations. In one case we wrote the right side x, in another case we wrote this without x 0. So same is the case here. So it gives two parts. This solution contains solution of first equation, which is this, contains two parts. One is y is equal to u plus v. Yes. The solution part u, the part u is called complementary function, usually denoted by CF, complementary function, which contains, and this part which contains n arbitrarily constants. This part contains actually n arbitrarily constants, or we may use n independent constants. Remember this also. And second part of solution, what is that? It is v. Second part of the solution is v. What about this v? Will be called, is called particular integral. This will be called what? Particular integral, that is pi. This will be called particular integral, which is free from arbitrarily constants. This part, particular integral, does not contain arbitrarily constants. So we have two parts. One is the complementary function CF, another is the particular integral. So we can write solution of first is as y is equal to CF plus pi. In some books you will see y is equal to CF, complementary function, plus particular integral. And I have told you what does complementary function stands for. Make right side 0, solve this, get the solution, involve there the number of constants equal to the order of the differential equation, and this particular integral we have to find out it, keep it x, but we have not yet described the method for finding out the particular integral. There, when we reach there for finding out the particular integral, we will give you different methods, different rules or cases, because this x is a function of x. Sometimes it can be algebraic, it can be trigonometric, it can be exponential, it can be logarithm. So we will give there you the rules how to find out the particular integral. That is the second case. Now this is the general thing, how we find out the solution in case of the differential equation using y is equal to complementary function plus particular integral. I think you have understood this. Now let me come to symbolic operator, symbolic representation of the differential equation. What we mean by symbolic representation? this is we use symbolic operators, or you may write symbolic representation of linear differential equation. How we do it? We define this way. In the derivative symbol that we use, dy by dx, this is your derivative symbol that you have been using from since the differentiation. The symbol here, d by dx, this is called here operator. This will be called operator. We define this operator symbol. We use the operators. It is just to write the differential, given linear differential equation in a short form. That is, this helps us to simplify the roots, to write the solutions of the differential, this complementary function in a simple way. We use this. We use the symbol for d by dx. We use d, capital D. We replace d by dx by capital D. When you have d2, second order derivative, not y involved here, d2 by dx square symbol, it is an operator, we use d square. Similarly, when you have d3 by dx3, you will use d3 or d cube, you may write, capital D. Similarly, proceeding this way, you can write dn by dxn as d raised to power n. These are the symbolic operators that we use, and on the basis of this we will write the differential equation, this linear differential equation in a symbolic representation. Then we will define it as auxiliary equation, what we mean by auxiliary equation, and how we find out the roots of this auxiliary equation and what those roots represent. That is the thing. I have given you everything in this general form, so that you are in a position to understand each and everything. Now come here, you can write, you have on the basis of this symbolic representation of linear differential equation of nth order. Okay, again I consider d and y dxn plus p1 dn minus 1 y dxn plus p2 dn minus 2 y dxn minus 2 plus pn minus 1 dy by dx plus pn y is equal to 0. I take, these are the, I have already told you in the beginning. Now we will be dealing with this such equations with constant coefficients, p1, p2, so on, pn minus 1, pn are constant coefficients. Now you have come to know we can write it in symbolic representation as per the previous definition. So it is symbolic representation is symbolic representation is, what is this now? It is d and y, because we use d and dx and d, not y. Y will be there as it is, plus p1, this is your d n minus 1 y plus p2, this is d n minus 2 y plus p n minus 1 dy plus p n y is equal to 0. This is dn plus pn dn minus 1 plus p2 dn minus 2 plus, these are the constants, pn minus 1 d plus pn y common is equal to 0. Now you look here, this is this expression whole is a function in d. This is now some function in d of what order? Of order n, because the highest power of d is n. So we write this in this way: f of d y is equal to 0. We write in this way: f of dy is equal to 0, where what is our fd? It is equal to, it is d power n plus p1 d power n minus 1 plus p2 d power n minus 2 plus so on to pn minus 1 d plus pn. This is called the some function. It is function in d. This is the symbolic representation of this differential equation now. So sometimes you write now directly f of dy is 0 for second equation in the theorem. F of dy is equal to x when you have right hand side this when you have right hand side what is called this the some function of x. Okay, this is the now on the basis of this we define auxiliary this equation. Auxiliary equation is actually when we make this, it is sometimes called also characteristic equation of this operator d. Sometimes we define it characteristic equation, but here we will give the name auxiliary equation. Auxiliary means helping equation. It is the equation that helps you to solve the linear differential equation. So mathematicians have named it auxiliary. So f of d we take equal to 0, solve f of d, that means we take this equal to 0. When you take this equal to 0, treating this d as some algebraic quantity, d we take as, say when we take it algebraic quantity, that means x raised power n p1 x raised power n1, then we solve this equation. Actually when this is a nth degree equation in d, it will give you how many values? N values. It will give you n roots, and those roots will be called the roots of the auxiliary equation. Then we have the roots can be now different. Sometimes the roots are all different, sometimes the roots are equal, some are equal, unequal, sometimes the roots are complex, the roots sometimes will be this repeated. So when such are the cases, we will give you the method how we write in that case the complementary function. That because solution has now two parts, one part is the complementary function and one part is the particular integral, and this is the main part of the solution, and this gives you what? Complementary. This gives you the roots, and roots help you to find out the complementary function. That I will tell you next. This third lecture will be, in third lecture we will discuss now auxiliary equation, the solution of auxiliary equation, and when we get the roots of the auxiliary equation, how we write down the complementary function. Now we are coming closer and closer to the method how to solve the linear differential equations of any order. Let it is order be. Now in some syllabuses there is mentioned that linear differential equations of second order. That means they have to confine on second order only, when we can solve third order, fourth order, fifth order, so on. So I hope you will follow this lecture, you will revise this, and next we will meet again in lecture number 3rd. There we will be discussing auxiliary equation and its solution. Then we will come closer to how to find out the complementary function. Thank you very much. I hope you have understood this lecture. Wait for the next, and till then, thank you very much.